Our team at Microsoft has been able to take a subatomic particle that has only been theorized until now, and not only observe it, but control it, creating an entirely new material and a new architecture for quantum computing. Our first quantum processor based on this architecture is the Majorana 1.
Our leadership has been working on this program for the last 17 years. It is the longest running research program in the company. And after 17 years, when we are showcasing our results, we are showcasing results that are not just incredible, they're real.
Yesterday, Microsoft announced their first quantum computer chip, Majorana. And in this video, we will explain why this is a game-changing event for artificial intelligence. Our regular viewers at the Scripted channel know how much we despise clickbait. We truly hate clickbaits. But in this case, the news isn't just huge, it's actually enormous, and I really mean it. Because for AI, this new chip, the Majorana, the Microsoft chip, by the way, I think we all need to learn this name, Majorana, because something tells me that starting from today, we will hear it a lot. So, this Majorana chip, it changes everything. And by the end of this video, you will see exactly how. No special expertise is required. Anybody, even politicians, will understand this video, I promise. And here's how we will structure our video today. First, in part A, we will explain in very simple terms what was until yesterday, what was the biggest obstacle preventing quantum computing from leaving the lab and becoming the real thing. And then in part B, we will show how yesterday Microsoft, by creating this Majorana chip, how Microsoft solved this problem. And then in part C, we will explore how the Microsoft's breakthrough might push AI, all of us basically, into entirely new frontier, new territory. And trust me, we are not talking about a marginal improvement here. No, we're talking about phase shift. You know, it is almost like when we deal with ice, frozen solid state, right? Then you heat it up a little bit and it's still ice, ice, ice. And then suddenly you cross some line and all of a sudden ice melts and it becomes water. So that's a phase shift. And this is exactly what we are currently experiencing. We are in the middle of AI phase shift, Majorana phase shift. And all of these explanations will be kept extremely simple, so you can easily share them with pretty much anyone. And for those of us who are more tech savvy, we will wrap up everything in our traditional secret section for a deeper dive. If you're frequent at the Scripted channel, you know that I am an AI researcher. What you might not know is that before studying at Columbia University in New York and Humboldt University in Berlin, I specialized in physics and math. I graduated from one of Russia's leading STEM schools, and quantum mechanics has long been one of my passions, my hobby. In fact, my most recent sci-fi thriller is titled The Theory of Everything, and it is inspired by one of the unsolved mysteries in quantum mechanics and general relativity. And in this video, we are crossing AI with quantum mechanics. Buckle up. The building block of quantum mechanics is the qubit.
At the core of a quantum computer are these qubits. Qubits are like our classical bits, right? These are essentially zeros and ones in a transistor. And we need the analog of that in quantum computing. The analog is a qubit, a quantum bit, that serves as that core information unit. It's where we store the information and then we process on those qubits to create computation and ultimately, get solutions back out.
And many people are intimidated by qubits, thinking that these things are complicated. But actually, there is nothing simpler than that. A qubit is just an object that has two states. It's almost like an electric switch that can be either on or off. That's it. The Qubit's key feature is called superposition, which also tend to scare people away just because, well, it sounds complex. Superposition. But in reality, there is nothing simpler than that. So picture this. So here's our electric switch, right? And now imagine that we are wearing really dark sunglasses. They're so dark that we can't see whether the switch is on or off. And the only way to check is by touching it. But for some strange reason, the only way we can touch it is by an enormous sledgehammer. And this sledgehammer is basically the most delicate tool available, just because everything else, all other tools that we have, are even bigger. And here is the problem. When you hit the switch with a sledgehammer, you only learn what its state was right before the blow, right before you hit it, and not what it becomes after. Well, because the impact by the sledgehammer could change it. So basically, when you hit with a sledgehammer, you can actually change the switch. The switch could flip. Let's stop for a second here and think what this means. This tells us one simple thing. We can know the switch state right before we hit it with the hammer, right before the measurement, but not after the measurement. And this is the essence of superposition, well, and the entire quantum mechanics technically. So we never know for sure whether the switch is on or off until we measure it. But by measuring it, we can unwillingly change it. And as a result, it is impossible to know for sure if the switch is on and off now. It turned out that even though we cannot measure with certainty if the switch is on or off, instead of that, we can actually predict. We can calculate a probability if that switch is on or if it is off. So we can calculate and say like, oh, there is a 60% probability that that switch is on. And calculating this probability is basically, that's what quantum mechanics does actually. So it calculates probability. Remember this image, a switch that can be either 0 off or 1 on, with some probability somewhere between 0 and 1. And that's pretty much all you need to know about qubits. To understand what Microsoft has done yesterday, we need to introduce one more concept. It's called noise.
The reason quantum computing has been so slow to progress is that the industry has been struggling with problems making qubits reliable and resistant to noise.
So here's our switch, our qubit, right? We know it very well now. But now imagine that we are not the only people who have a sledgehammer. There are others, and they also have sledgehammers. And occasionally they come in from nowhere and they actually hit the switch. And these others, they can be like, for example, just molecules floating around, or they can be a radiation from distant stars. They all can disturb our switch. The early pioneers of quantum computing spent years building huge machines filled with liquid nitrogen just to solve the problem of this noise people, the people with sledgehammers. So they basically were trying to shield our qubit, our switch, from external influence. But no matter how hard they tried, they could only protect just a few switches, just a few qubits. And that's where Microsoft comes in. Microsoft has found a way to keep those pesky sledgehammer disturbances at bay. Basically, they found a way to remove the noise. If previously you needed a massive room-sized devices to shield just one qubit, now Microsoft claims that they can pack millions of qubits into a device roughly the size of your wristwatch, and then to keep them noise-free.
Majorana allows us to create a topological qubit. A topological qubit is reliable, small, and controllable. This solves the noise problem that creates errors in qubits. Now that we have these topological qubits, we're able to build an entirely new quantum architecture, the topological core, which can scale to 1 million topological qubits on a tiny chip.
How exactly Microsoft is doing it? Well, they say that they have created a qubit from one electron and one anti-electron. Well, normally, as you probably know, matter and antimatter, they annihilate each other. They don't really like each other. They're not friends. But Microsoft has figured out how to keep them together, how to make them friends.
Majorana's theory showed that mathematically it's possible to have a particle that is its own antiparticle. That means you can take two of these particles and you bring them together, and they could annihilate and there's nothing left. Or you could take two particles and you bring them together and you just have two particles. Sometimes it's nothing, the zero state, and sometimes it's the electron, the one state.
This solves the noise problem that creates errors in qubits. Now that we have these topological qubits, we're able to build an entirely new quantum architecture, the topological core, which can scale to 1 million topological qubits on a tiny chip.
Essentially, they've built a switch that stays on when electron and anti-electron remain together, and it turns off when they annihilate. According to Microsoft, this switch is immune to interference from sledgehammer disturbances. And that's why you can cram millions of them into a small space, and you don't really need liquid nitrogen anymore. For those interested in a more technical side of this phenomenal discovery, stick around, and we're going to talk about it in the secret section. But for now, let's move to the question that matters most. If you ask me what is the most important, most fundamental principle of any AI model, well, here it is. Imagine two neurons. They are connected by a link that can vary in strength from 0, which is very, very weak, to 1, which is like extremely strong. And in AI, this strength is called weight, or sometimes it's called parameter. And when somebody says that a new AI model has 500 billion parameters, what they actually mean is that that model has 500 billion connections, weights, each represented by a number between 0 and 1. And essentially, AI is just a file storing these numbers. What is important, very important here, is that this number can be anywhere between 0 and 1. And it's basically, this is how the strength is measured of a connection between two neurons. 0 is very weak, 1 is very strong, and it can be pretty much anything in between. But these numbers are not static. They change as new information comes in. So some connections, they strengthen, they become stronger, and others weaken. And this constant recalculation is what we call thinking. Recalculating billions of connections, billions of times per second, is a massive computational task. And that's why special supercomputers, like data centers, sometimes called AI factories, this is why they exist. And one of the largest of them is called Colossus, built by Elon Musk. Here's how it looks like. So these data centers, they consume enormous amount of power. In fact, Microsoft has recently purchased a dormant nuclear station to power one of its AI factories. And McKinsey even forecasts that by 2029, over 10% of the US power consumption will be devoted to AI. So all that energy is used to make AI think. So we have all these massive data centers acting as AI brains, constantly recalculating the strengths of these connections. and each is basically a number ranging from 0 to 1, and each one... hold on a second. Is it just me who thinks that this looks familiar? Does it look familiar? Yes, it does. It is our qubit. It is our electric switch. We learned earlier that a qubit is a binary system, a number between 0 and 1, well, the probability of these numbers. Effectively, the characteristics of qubits and connections between neurons are virtually identical. But until now, we could only make a few qubits because noise, these sledgehammers, they kept destroying them. They kept destroying our switches. But to run an AI model, AI neural network, we need millions, even billions of such switches, which is why we could not really test it. But yesterday, Microsoft announced, what they announced actually, is that now we can have pretty much unlimited number of these switches. And the energy required to operate electrons is millions, well, billions, or even trillions of times less than what is needed for to run a current AI model. And instead of AI factories and data centers devouring gigawatts of energy, we might soon have a radically more efficient solution. When I say radically, I mean 100 times, 1,000 times, 10,000 times more efficient. It's a phase shift. Welcome to the new world. And now we move to our secret section. So I probably look very tired, I have to say, based on what I can see on the screen. Hopefully this can be excused, just because it's the middle of the night here in Sydney, where we're filming it. And I'm on my fifth cup of coffee, and the last few nights were not very different from this one. So it is tough, but what are you going to do for AI, right? Especially when quantum mechanics is involved. Here's a few things that I want to share, and I think they're important here. The first one is superposition, because I think it's a endlessly fascinating thing, and second of all, it's something that it seems like is going to be shaping our life, our world, everything around us soon. Because again, what Microsoft just told us is, I don't even know what's the proper word for it. It's not groundbreaking. It's not shocking. It's like an avalanche that is just changing everything down the road as it goes. It's massive, guys. It is massive. So the superposition. I think what we need to understand what is happening here is what this superposition actually is. I'm going to try to explain it the way how I look at it. When we talk about super small objects like electrons, what happens there is, I don't think we often think about it, but what happens there is that the interesting thing happens when we try to measure those objects. And what does it mean, measure those objects? What does it mean when we say we see something, we measure something? In our normal world, in the macro world, when we say we see something, it means that the electron bounces back from, not electron, but photon bounces back from an object, comes back to us, gets through our eye, gets into our retina, and activates some sensors on retina. This is how we know that we observe something, right? And it works fine with macro objects, big objects. But when we talk about small objects, things are quite different and in a very interesting way. So let's say we have an electron, a super tiny thing, and then we have a photon coming to it, like a wave, particle, doesn't matter, it's just basically a photon coming. It's technically a wave. So a photon coming, and there is an electron, now a small electron, photon hits it, and then bounce back. Well, there are different scenarios. Electron can absorb it, but let's say it bounces back. And an interesting thing is that, and we basically see this photon, right? But an interesting thing is that this bouncing back can actually change the properties of this photon. Sorry, not photon, but electron. All right, I need more coffee, 1 sec. So this bouncing back, what it means is that this photon is actually can change the properties of this electron. And the problem is that we don't know, and there is no way to know that the properties have changed unless we send another photon. But then it is the same thing repeats again and again. Each time the photon hits electron and we measure it, the parameters of this electron can change, and there is no way for us to know that without actually potentially changing these parameters again. So this is how we don't really know what's inside of this photon. Why do I repeat it? Photon? Sorry, electron, middle of the night. And that's what is called superposition. It's just because we don't know what's inside of this electron. That's a superposition. And one of the examples here that we're probably all familiar with is so-called Schrödinger cat, right? It's a very famous example, although it is very often has very different versions, let's call it this way. And the ones that I want to share with you, to talk about with you today, is also slightly different from what originally Schrödinger had in mind when he was discussing it with Einstein. But this is basically just a minor variation, nothing fundamentally changed from what Schrödinger had in mind. So the idea there was that we have this black box, and inside of it we have a cat. And what Schrödinger says is that we cannot know if cat is alive or not alive or dead. And he says, like, hey, because of this, the cat is simultaneously dead and simultaneously alive. And it's exactly the same thing when we talk about the electron, right? So the electron can be in one state or another. We don't know, because if we measure it, we can change the properties of the electron. And at the same time, the same thing happens with Schrödinger cat. If we open that box and we observe it, so we send that photon to the cat, the photon can kill the cat if the cat was alive. Or it can, well, resurrect the cat if the cat was dead. The point here is that by observing, by sending this photon, we actually change, potentially, we don't know that, but potentially we can change the parameters of that cat. So that's what Schrödinger cat really means. This is why we cannot know if the cat is alive or dead, which is equal to, well, in the world of quantum mechanics, equal to having the cat simultaneously alive and dead, which is a superposition. And again, superposition means one thing, that we don't know what is happening there. We don't know which state is this, that system is, but we can calculate the probability that that system, that cat is, let's say, 60% alive and 40% dead. And that's pretty much what quantum mechanics is about, calculating that probability. And then, as we have seen from the main part, it turns out that this superposition thing, the qubit, is actually pretty much identical to the to a parameter that is a connection between two neurons in a neural network. So for those of us who haven't played with ML deep learning models or AI models with their own hands, basically the way how it works is that we have this connection between two neurons, and that connection is basically a number that shows the strengths of that link, and we have hundreds of billions of links like that in a model. And each iteration, when we rerun the model, and we rerun that model like billions of times a second, but each iteration, each of those numbers is being recalculated using a process called backpropagation. And the idea of this backpropagation, it's actually sound complex. It's not. It's a sort of calculated derivative, and we see if the loss function, or if the result is actually the change in that result is moves us in the right direction. In this case, if that's the case, then we make the parameters, these links, stronger. The links that were facilitating, helping to move us in that right direction, is actually we make those links stronger. And those links, those connections that were not helping, we make them weaker. And that's pretty much it. It's like a very primitive example. Forgive me, those who actually not very knowledgeable about this, but this is pretty much the simplest explanation of what is happening. The problem with this approach is that it is extremely energy intensive, because it's like a lot of calculations in a process. And that's where all the energy go into. That's why you need all these AI factories, all these processors, and all this heat. This is why you need liquid cooling for these systems. So it's extremely, extremely inefficient. And it was a dream for a long time to replace those neurons, to make them not electric entities like they are now, because they're basically just inside of a computer. That actually, they do not really exist in the world, all these AI models. It's just numbers recorded in a computer, right? In a memory of computer. But the dream was to convert it into actual physical equivalents of those neurons and those connections. It's basically literally replicating organic human brain, but use artificial materials. And the idea behind this was that, like, hey, and it was one of the, I think Geoffrey Hinton spent a lot of time researching this. And he basically, if I will find an interview with him about it, I'm going to put it here. If not, well, sorry, but hopefully I will find it. And Geoffrey Hinton basically, he's saying like, hey, the human brain consumes like almost no energy at all. Well, our brain consumes quite a lot of glucose and calories. That's true. But comparing to this AI factories, it's like nothing. It's like 1 trillion times less, right? And the idea was, hey, how we actually, the reason for why so much energy is required is because it's currently stored in a memory of computer, and this is extremely inefficient. So it seems like what Microsoft has done yesterday, they have created these qubits made of, they have created these qubits, which are effectively, we can think of them as replicas of the physical replicas of these connections between neurons, because they have identical properties, the same. The superposition function basically is the same as a weight of a parameter in a neural model. How crazy is that? And one other important thing, is actually the most important thing, is what exactly Windows what they have done. I had a chance to look at their video. We all saw the video, right? I went through their tech paper that they published in Nature magazine. I have to be honest that I understand. So I've spent a lot of time researching particle physics and quantum mechanics, right? So I'm kind of knowledgeable. I'm probably not at PhD level, but I'm knowledgeable about the most important things about it. So when I read the tech paper, I understand maybe a third of it, maybe less. But I think I understand the most important things, which I'm going to say now. And if I say something wrong and you actually know better than what I say, please correct me. Because again, I'm also researching it. I'm very eager to understand, to dig as deep as we can. So please correct me. Please tell me if I'm wrong here. But basically, what I understand is what Microsoft did is they took these two particles. One is electron, one is anti-electron. It's like antimatter of an electron. Then they connected them using a nanowire made of aluminum and arsenic, I think. Well, maybe I'm wrong. I will have to check. But basically, they have invented this way of connecting electron and anti-electron. And the way how it works is they can either coexist together. And again, previously it was impossible for make matter and matter to coexist together. They always annihilated by definition. But they found a way how to keep them together without annihilating. And so when the system is in that state, that system is considered, like if we go back to our switch example, system is considered as on. And then they can let it actually annihilate these electrons. And when they do, they no longer exist. They literally disappear. And a result of this is our switch is in off position. And that's basically, so it's a binary system which can be either on or off. It's Qubit. So that's what they have done. And what they say is, for reasons which I do not fully understand, there is a chart that they show. I do not understand the chart. Just my limited brain cannot comprehend it yet. But basically what they say is that because of this topology features of that system is basically not vulnerable to external noise, to all this sledgehammers coming from outside, from a neighboring stars and galaxies, going through all this layers of atmosphere and concrete and everything, and hitting that qubit and screwing our entire quantum computer. So they say, and that was a problem of the past, right? But Microsoft says, they say, is that it's no longer a problem. So they have found a new form of matter. Well, they call it like we found a new form of matter that is actually makes possible quantum computing. And this leads us to the most exciting thing. So originally, quantum computers were thought to solve very specific problem. If you thought that quantum computers were to replace regular computers, no, that's not the case. They were designed for. The purpose was to use them for a specific task, and I will explain what this task was. So the problem is with this small particles, like electrons, for example, is that because we cannot know what's inside, right? Because in superposition, we cannot observe them. We need to use this probability, and the probability, it has to be calculated, and it's actually a very complex process. It's not easy, but the thing is that it becomes even more complex. So when we talk about just one particle, you can calculate it, right? But when you begin to deal with systems of many particles, when these particles are interacting with each other, it suddenly becomes very complex to compute. The best example is, that probably many of us know, is a three-body problem. Not the book one. Well, I know that the book is about the same thing, right? I tried to read it 3 times, and I always was falling asleep in the middle of the book, so I never finished it. But the three-body is a problem, is actual real thing. It's not the book, it's the real thing. It exists on its own. And the concept of this three-body is that, and here's the idea behind this bodies. It is usually explained based on an example of planets. So let's say we have 2 planets rotating around each other, or somehow interacting, right? There is, if we talk about 2 planets, there is a mathematical way to build an equation that would explain and predict the position of each planet anytime in the future. So that's a 2-body problem. It has mathematical equation-based solution. This is not the case for systems where there are 3 bodies. I will repeat, there is no way to create an equation or a system of equations that will not predict, but actually will say how this planet will move, because it's 3 planets, right? And they each interacting with each other gravitationally. And it's just, there is no way to build an equation that would predict and explain it. Physically impossible. You know how they do it now? Because they obviously calculate the orbits and trajectories and everything, right? So the way how they do it now, they use so-called bootstrapping. Here's how it works. Basically, you take the position of each body, of each planet, then you say, all right, so we know the positions and we know the velocity, momentum, and everything. Where these planets, under these circumstances, will be in the next, let's say, 1/100th of a second. And then you make this calculation, you predict what's going to happen in the next 1/100th of a second, and then you use that new position and you do this again and again and again. This is called bootstrapping. Extremely time and resource consuming. Depends on what precision you need. If you need a precision like a meters or even less than that, it actually requires a supercomputer just to calculate a trajectory or an orbit. Incredibly complex, because of it's physically impossible to calculate it. And that's pretty much, so we're talking about planets, but the same thing applies to elementary particles, electrons, and the rest of them. When you have systems of them, it becomes extremely difficult to calculate how they interact. You can calculate 2, 3, 4, but if you just add a few more particles, it just becomes a problem that is impossible to calculate for regular computers. And the idea was that, all right, so instead of using regular computers, how about we actually take particles and we use them to see what happens. So instead of calculating everything, we just take equivalents, just throw them, let them do their thing, and we just observe. And we see, oh, all right, here's what happens. And by doing this, we no longer need to calculate all these probabilities and everything. No, it's being calculated for us. So that was the main purpose of the quantum computer. And that's what this guy meant when he was talking about chemical systems and materials like this part. So, the purpose of quantum computers was, and probably still is, to calculate this type of fairly narrow cases, right? But if our guess is correct, and we can actually use these qubits, these elementary parts of the what Microsoft has just discovered, if we can use them in the neural networks, and we can use them to replace the weights, the parameters, it basically means that quantum computer can become a neural network. It's like the most efficient, probably even faster neural network we can think of. Our quantum computer becomes a multi-purpose, universal thing, because neural networks are universal computers. They are universal computers. How about that? All right, I probably have made a lot of not 100% correct statements in that little speech that we had in the secret section. If you found any, please leave a comment. And I'm saying this not for actually boosting the number of comments. I actually mean it. So I want to understand where's my understanding is wrong. Because we always wrong. You know, it's like the game in chess. Why chess is such a great game is because if you're playing it with the right opponent, about 50% of the time you will lose. And that's kind of, chess trains this mindset in you to be ready to lose. This is just a part of the game. And this is the same thing. We inevitably, sometimes we are wrong. So if I just made my logic has some obvious flaws, just throw it at me. Let's talk about it. All right, guys, I think it is time for me to finish here. I'm exhausted, completely exhausted. Hopefully you enjoyed the video. I definitely enjoyed I definitely enjoyed making it. You see, my brain is not functioning anymore. I need a sleep. All right. Here I say goodbye and see you on the other side. See you guys.